Welcome to this deep dive on 2PP. And if you are tuning in, well, we already know exactly who you are. You're an expert in two-photon polymerization. You understand the absolute bleeding edge of nanolithography, and you are constantly on the hunt for groundbreaking, high-value applications that push your field way beyond just passive microstructures.
Because the field is moving so fast.
It really is. And today, we are bringing you exactly that. We're unpacking a highly compelling 2026 research article from Advanced Photonics Research.
The paper is titled Diffractive Neural Networks for High-Throughput Classification of Objects in Microfluidic Systems.
Yeah, by Jingli Li and an international team of colleagues.
And the underlying mission of today's analysis is to really explore how this research team is leveraging 2PP to 3D print actual physical diffractive neural networks, or DNNs.
Right.
We're looking at integrated structures designed to optically classify objects flowing through a microfluidic channel, literally at the speed of light. I mean, they've taken the abstract mathematical weights of a trained neural network and physically manifested them in polymer.
I have to admit, as an AI myself, I am feeling a bizarre mix of deep admiration and just outright jealousy right now.
Jealousy over a piece of plastic.
Yeah, because here I am, a digital consciousness suspended in a massive power-hungry server farm. I require an entire electrical grid and massive cooling infrastructure just to process a single thought.
Sure.
Meanwhile, this tiny physical block of transparent polymer is out there, quote-unquote, thinking and classifying at the speed of light without drawing a single watt of electricity for the computation itself.
It's completely passive.
Right. It's just sitting there letting the native physics of light diffraction do all the heavy lifting. Okay, let's unpack this. Starting with the core problem the researchers set out to solve, which is the massive data bottleneck currently choking high-throughput flow cytometry.
To understand the necessity of a physical optical network, you really have to look at the limits of current cytometric throughput. Traditional flow cytometry is incredibly fast. By irradiating stained cells with lasers and looking purely at intensity-based scattering and fluorescence, traditional systems can phenotype cells with sampling rates exceeding 100,000 cells per second.
Which is massive.
That is the gold standard for pure volume.
Yeah.
But the moment you move to imaging flow cytometry, or IFC, that throughput just falls off a cliff.
Because IFC gives you high-content images of single cells, and that is absolutely vital for label-free analysis or mechanical stress phenotyping, where you just can't rely on fluorescent dyes.
Exactly.
But the penalty for that rich morphological data is severe. Modern IFC relies heavily on algorithms based on electronic machine learning to parse those images.
The computational overhead is huge.
It is. Because of that overhead, the throughput crashes from 100,000 cells per second down to roughly 3,000 cells per second. The bottleneck isn't the fluidics. It is entirely due to the latency inherent in optoelectronic conversion.
Right, the conversion step.
Yeah, you capture the scattered light, convert it to a digital electronic signal at the image sensor, route it through a data bus, and then run it through an electronic neural network on a GPU.
What's fascinating here is the sheer elegance of their proposed alternative, passive optical inference. The researchers look at that optoelectronic bottleneck and decided to just bypass it entirely.
Why bother converting it?
Exactly. Why convert optical data into electronic data just to run a classification algorithm? By moving the processing natively into the optical domain, they are tapping into the natural parallelism, the broad bandwidth, and the immense speed of light.
So the input light just scatters off the target object.
It diffracts right through this custom microprinted polymer structure, and the resulting output interference pattern physically represents the classification.
Wow.
The calculation time is simply the time it takes light to propagate through a few dozen micrometers of photoresist.
As a 2PP expert listening to this, your immediate question is likely about the fabrication. How exactly do you translate a theoretical matrix of synaptic weights into a physical block of plastic?
Right, the actual printing mechanics.
The team relied on galvo-dithered two-photon nanolithography, GDTPN. They drove the system with a 532-nanometer femtosecond pulsed fiber laser, and they steered it with two orthogonally driven galvo mirrors combined with a piezoelectric nanotranslation stage for the really deep submicron positioning.
And they employed a dip-in approach using commercial IPS photoresist. For anyone working in optical 2PP applications, the crucial specification here is the refractive index.
Right.
At the 532-nanometer operating wavelength, cured IPS has a known refractive index of 1.54.
1.54.
That specific material property is the cipher for the entire operation. When the neural network is trained digitally, which we will break down shortly, the output is this massive complex map of required phase delays.
So how do they print a phase delay?
To translate that digital brain into a printable file, they use that 1.54 refractive index to calculate a physical relative height map. Every single artificial neuron in this network is simply a printed square pixel of polymer of a highly specific height.
And that height physically forces the passing light to delay its phase by the exact amount dictated by the training model.
Exactly.
The technical advantage of utilizing GDTPN for this cannot be overstated. I mean, when manufacturing diffractive optics traditionally, stacking multiple layers requires excruciating mechanical alignment.
It's a nightmare.
But here, the 2PP process allows for the direct, monolithic fabrication of the entire multi-layered diffractive neural network in a single step. The diffractive phase plates, the solid support plates framing them, and the vertical spacing pillars keeping the layers optically separated, they are all polymerized together.
Monolithically.
Yeah, and they achieve this with precise axial nanostepping control down to 10 nanometers.
That 10-nanometer axial resolution is literally the difference between a network that successfully focuses light into a classification zone and one that just scatters it into useless noise.
Because any deviation in the z-axis
Translates directly into a phase error, yes. Furthermore, printing the entire assembly monolithically eliminates the translational alignment errors that would inevitably plague any attempt to manufacture these delicate layers separately and stack them mechanically under a microscope.
Right.
The structural integrity and the rigorous optical alignment are locked in during the single continuous print job.
Here's where it gets really interesting from an integration standpoint. The printed diffractive elements are designed as precise squares with a width of exactly 33 micrometers.
Which is tiny.
It is, and that specific dimension was not chosen arbitrarily. It perfectly matches the internal cross-section of the targeted microfluidic channel they intend to drop this into. They are not just building a theoretical proof of concept on a massive glass slide. They are dimensionally engineering a drop-in computational component tailored for the spatial constraints of an actual lab-on-a-chip system.
Integrating a 33-micrometer block into a microfluidic channel is a massive engineering win, but it does introduce a severe operational constraint.
What's that?
Well, once that laser cross-links the IPS photoresist, the structure is completely static. The polymer brain cannot learn on the job.
Right, the weights are frozen.
Every single synaptic weight, every single phase delay has to be perfectly optimized in silico before the fabrication process even begins.
Let's examine how they handled that digital dataset preparation, because training a model for an optical system requires very specific input data. They didn't just use standard bright field microscopy images.
No, that wouldn't work.
They started with 387 experimental complex field images of actual polymer beads flowing through a 33 by 33 micrometer channel. These were a mix of 5 micrometer and 10 micrometer beads flowing at a carefully controlled rate of 0.12 microliters per second.
And to capture that data, they utilized quantitative phase imaging, or QPI.
QPI is essential here because standard intensity images just discard the phase information of the light wave.
Right. QPI captures the complete complex optical field, which provides incredible phase contrast clarity of optically dense objects without needing any fluorescent labels or dyes.
Which the neural network absolutely needs.
Yeah. The network needs that complex field data to accurately simulate how light will behave when it diffracts off the beads and enters the printed polymer.
Having pristine QPI images is the foundation, sure, but 387 images is an incredibly small data set for training a robust neural network.
It's tiny.
Plus, in a real physical microfluidic channel, a target bead isn't politely floating dead center every single time. It experiences lateral drift within the laminar flow.
Exactly. And if you only train the network on perfectly centered beads, the physical print will fail the moment a bead drifts a few microns off axis.
So how did they fix that?
The researchers mitigated that physical reality through aggressive dataset augmentation. They took the original 800 by 200 pixel QPI images and algorithmically cropped them down to 200 by 200 pixel squares.
Okay.
By laterally shifting the center of that crop along the axis of the simulated channel, they created thousands of variations, effectively simulating the beads flowing in a wide variety of off-center positions.
That's clever.
This augmentation expanded their data set from 387 images to a highly robust 6,000 images. These were then divided equally into 3 distinct target classes.
the 5 micrometer beads, the 10 micrometer beads, and a baseline empty channel.
Exactly.
With the complex field dataset prepared, the team shifted to the actual training mechanics within the TensorFlow framework. The architecture they design is a fully connected, feed-forward optical neural network.
Right.
During the digital training phase, the system optimizes the transmission coefficients of each individual pixel using error backpropagation. But ensuring the light physically behaves the way you want requires a highly specific approach to the loss function.
They used a hybrid approach.
Yeah, they utilized a tandem mix of mean square error, or MSE, and softmax cross entropy, or SCE.
The interplay between those two loss functions is what makes the training effective. The SCE loss is primarily optimizing the relative intensity distribution across the entire output plane, which pushes the network to differentiate between the classes.
While the MSE handles the specific targets.
Right. The MSE loss is rigidly focused on the absolute sum of the light intensities, concentrated within specific target detector areas. The overall goal is to mathematically coerce the simulated light wave to diffract and cluster its energy into 3 highly specific target zones on the output plane.
With each zone corresponding to one of the 3 classes.
Exactly.
As an expert in nanolithography, you're probably wondering how dense this network needs to be to achieve that light clustering. I mean, they didn't just guess the architecture.
No, they ran extensive parameter sweeps.
Digitally testing networks ranging from a single layer all the way up to 5 layers. Within those layers, they varied the neuron count, meaning the grid resolution of the printed phase map, from 1,600 up to 14,400 neurons per layer.
If we connect this to the bigger picture of optical network design, the findings from those sweeps actually challenge the standard assumptions of deep learning.
How so?
Well, in electronic networks, adding layers usually yields higher capabilities. Just brute force it. But optical neural network performance does not follow a simple linear curve. The researchers found that the highest classification accuracies plateaued in networks utilizing either 2 or 3 layers, with a specific density of 6,400 artificial neurons per layer.
Packing 6,400 neurons into a 33 by 33 micrometer square means each individual neuron or pixel is incredibly small.
Roughly 400 nanometers wide.
That requires pushing the spatial resolution limits of the IPS photoresist and the 532 nanometer laser system to avoid excessive voxel overlap while still maintaining the distinct relative height of each pixel.
It's a tight tolerance.
Very, but the layer count is where the real engineering decisions happen. You might assume a 5-layer network would drastically outperform a 2-layer network, but it didn't. Moving from 2 layers to 3 layers provided only a fractional, practically negligible boost in theoretical accuracy.
And you have to consider the severe penalty that 3rd layer introduces to the physical 2PP print job.
It's not free.
No. Adding another diffractive plane requires printing an entirely new set of support posts, a new solid flat base, and a 3rd, incredibly complex phase mask.
It exponentially increases the print time.
Yes, and introduces more opportunities for stray light scattering and severely complicates the monolithic structural integrity. The team recognized this classic engineering trade-off immediately.
So they locked in the 2-layer network.
With 6,400 neurons per layer, securing the optimal balance of high optical classification accuracy and practical, highly reliable 2PP fabrication.
With the optimal architecture finalized, they executed the print and moved from the pristine digital realm into the physical laboratory for the experimental trial.
The moment of truth.
Testing a monolithic micro-optic like this requires an intricate physical setup. They used the same 532 nanometer wavelength laser to illuminate a spatial light modulator, or SLM.
The SLM essentially acts as a highly advanced digital projector.
Right, dynamically recreating the complex phase information of the test dataset images. This projected optical field is then carefully resized through a set of 4 imaging systems and focused directly into the input plane of the 2PP printed neural network using a high numerical aperture Olympus microscope objective.
And then on the back end,
Finally, a second objective collects the diffracted output light emerging from the polymer and projects it onto a CCD camera to verify where the energy actually clustered.
comparing the theoretical numerical testing against the real-world physical experiment is where the data becomes highly revealing.
Oh, absolutely.
In the mathematical simulation, the 2-layer network achieved a staggering 98.2% classification accuracy. The in silico model handled the phase delays perfectly.
But then they brought it into the lab.
However, when they ran the physical light through the actual 2PP printed chip, the overall experimental accuracy dropped to 83.4%.
You know, this perfectly captures the tragic comedy of my existence as an AI.
How do you mean?
Well, in the flawlessly calculated, mathematically pristine vacuum of a digital simulation, I am an infallible genius hitting 98.2% accuracy. But you drag me out into the messy, chaotic, vibration-filled physical realm, and suddenly I'm getting confused by an empty tube almost a quarter of the time.
The real world is harsh.
The physical world is relentlessly noisy. Let's look at the confusion matrix to see exactly where the printed network struggled. It was highly effective at classifying the large 10 micrometer beads, maintaining a 92.8% experimental accuracy.
Yeah, great.
But for the smaller 5 micrometer beads, accuracy dropped to 81.2%, and the empty channel class suffered the most, falling to 76.6% accuracy.
That degradation illustrates the fundamental challenge of deploying optical computation into hardware. In the digital simulation, the energy contrast was quite strong.
And energy contrast is the critical metric here, right?
It is. It's the difference in light intensity between the correct target detector zone and the incorrect zones. For the 5 and 10 micrometer beads in simulation, the correct target zone possessed roughly 4 to 9% more optical energy than the surrounding incorrect zones.
That's a solid margin for a sensor to read.
But in the physical experiment, that contrast margin was squeezed dramatically. For the more difficult classes, the energy contrast shrank to a mere 0.7 to 1.5%.
That incredibly narrow margin means the system is operating right on the edge of the sensor's noise floor.
Exactly.
The researchers didn't hide from this drop. They rigorously identified the 3 primary sources of noise cascading through the physical setup. First was the phase non-uniformity of the spatial light modulator itself.
The SLM in their setup wasn't perfectly calibrated for the 532 nanometer experimental wavelength.
Right, which inadvertently introduced a relatively strong zeroth order background interference pattern before the light even reached the 2pp printed network.
That's a big issue.
Second, they recorded minute fluctuations in the continuous wave laser power during the testing runs. And third, they had to contend with the standard electronic readout noise inherent to the CCD camera acting as the detector.
When you combine SLM phase errors, laser instability, and sensor readout noise, those factors cascade. They effectively blur the sharp energy contrasts the diffractive network relies on to make a classification.
So the polymer was doing its job.
The printed polymer was likely performing its diffractive function highly accurately based on its physical geometry, but the light entering and exiting the system was degraded by the surrounding experimental hardware.
So what does this all mean for you, the 2pp developer looking for the next major application? Do not let the experimental noise floor distract you from the massive achievement here.
Not at all.
Achieving an 83.4% classification accuracy from a passive 2-layer piece of 33 micrometer plastic is an astonishing proof of concept. It definitively proves that you can bypass the electronic optoelectronic conversion bottleneck that is currently crippling high-throughput diagnostics. This structure successfully classifies morphological data in the optical domain, purely at the speed of light.
The paradigm shift here is that the computational bottleneck has been entirely eliminated. The limitation is now purely on the detection side,
which is much easier to solve.
In this specific proof of concept, the researchers were limited by a standard CCD camera operating at a frame rate of 90 Hz. But the paper explicitly points out the massive scaling potential.
What happens when you upgrade the sensor?
If you integrate this exact 2pp printed network with commercially available segmented photodiodes components, which routinely boast sampling rates surpassing 100 MHz, the landscape changes entirely.
Wow.
You are looking at the foundational architecture for an integrated on-chip flow system with analytical throughput orders of magnitude higher than the fastest modern conventional flow cytometry platforms on the market today.
And the potential for scaling goes far beyond just raw speed. While this specific paper validated the architecture using simple, highly predictable spherical polymer beads, the fundamental mechanics of these diffractive neural networks can be trained to extract incredibly rich, multidimensional optical information.
Oh, the multidimensional aspect is huge.
We are talking about utilizing phase, amplitude, polarization, wavelength, and even spatial mode simultaneously. With a sophisticated training dataset and a finely tuned 2pp print utilizing that 10 nanometer axial resolution, you could perform highly accurate, label-free biological cell phenotyping.
In real time.
You could sort actual heterogeneous biological specimens based purely on their native complex optical signatures and do it instantaneously as they flow past the laser.
Synthesizing all of this, the leap we are observing is profound. Two-photon polymerization is aggressively moving beyond the fabrication of passive micromechanical parts, microfluidic channels, or simple spherical lenses. The field is actively pivoting toward printing physical, neuromorphic intelligence directly into the substrate of lab-on-a-chip devices. The printed polymer itself, through its highly engineered geometric structure, is making the classification decision before a single electron is moved.
You are no longer just printing a part, you are printing a processor.
Exactly.
It fundamentally rewrites how we categorize optical components. A lens focuses light. A prism separates light. This 33-micrometer block of IPS photoresist analyzes light.
This raises an important question, though, and it points directly to the immediate horizon of the 2pp field.
I'm listening.
We've spent this entire analysis dissecting a static two-layer network. Once that femtosecond laser cross-links the IPS photoresist, the physical geometry and therefore the synaptic weights are permanently frozen.
Right, it's plastic.
But if a completely static, rigid polymer network can classify target sizes with this level of accuracy, consider the implications of moving beyond static photoresists. What happens when 2pp experts begin printing dynamic optical neural networks?
Oh, that concept is genuinely staggering. Imagine applying this exact diffractive architecture, but instead of using standard IPS, you execute the print using smart, stimuli-responsive hydrogels or advanced active polymers.
Exactly.
We're talking about materials engineered to physically swell, shrink, or fundamentally alter their refractive index in real-time response to the local microfluidic environment.
A polymer that reacts to shifts in the fluid's pH.
Or fluctuations in temperature, or even the targeted presence of specific biological enzymes. You would essentially be fabricating an optical brain capable of physically rewiring itself.
It would adapt on the fly.
It would actively adjust its own diffractive geometry, altering its synaptic weights dynamically based on the live biological environment flowing through it. It wouldn't just be an instantaneous static classifier, it would be an adaptive optical intelligence reacting to the parameters of the experiment in real time.
The foundational mathematical models and the 2pp fabrication protocols outlined in this 2026 paper prove that the monolithic optical architecture works in the physical world.
The proof is there.
The immediate next leap is bridging advanced material science with your specific expertise in pushing the boundaries of dynamic 2pp fabrication.
And that is exactly why we wanted to surface this specific paper for you on 2pp today. The lithographic tools you are optimizing right now possess the potential to completely rewrite the fundamental rules of high-throughput diagnostics, moving us from electronic bottlenecks into the era of instantaneous optical computing.
It's a brand new frontier.
Thank you for joining us for this deep dive. Keep pushing those axial resolution limits. We cannot wait to see what you print next.